Okay, it's time to begin. I don't see Ryan or Bridget. And here, Ann. The final exam. Or Cassie, who is feeling ill. And Jaron went to the bathroom. Okay, let's see. First of all, just a renewed plea. Anyone who has Monday afternoon open and would like to be a TA for Principles of Physics Lab, which is doing essentially the same labs that you've already done, just cut down. Lindsay wants us to do our labs their way. I need a TA and would love to have. Any one of you should be sufficient in the field. So please remember and talk to me if you're interested. Second thing, remember that the concept coach questions are due before class for the material that's going to be covered. So for today it would be all of 18 and then through 19.1 for the concept coach questions. And homework, don't forget that homework is due after every lecture, so there will be a homework due today. And with it being Friday, the homework is due about 5 minutes before sundown so that we don't have students working on their homework during the Sabbath hours. Everybody remember those things? Yeah. I mean, I don't want any shocks or surprises or what? Okay, a picture, just to get us a word that's going to come in later, ground. We talk about ground with electric circuits a lot. And ground really means what it sounds like. It means sticking a rod into the ground. I have a rod like that I pounded in my backyard, and then I have a wire that goes from there and grounds my satellite dish. So that, if lightning were to strike it, the charge would go through that wire into the earth rather than going into my satellite receiver and causing me problems. So this is the symbol used for ground. And it's really done by sticking a spike in the ground. So I just wanted to make sure I got that in there before I forget. Now a clicker question. This is a question that was in the concept coach questions, but incorrect. I'm glad to see people nodding. Yes, it was incorrect there. Because when I see incorrect questions, I'm like, no. When you're just learning and you're getting a negative feedback, that's not going to help. So, a particle with a positive charge plus Q is a distance r from a particle with a negative charge minus 2Q. The Coulomb force that the positive charge exerts on the negative charge is plus F, where F is the magnitude and the plus sign tells you the direction. What is the magnitude and direction of the Coulomb force that the negative charge exerts on the positive charge? Okay, I'll give another 5 seconds or so before I stop. Actually, everyone that's here is answered. I guess I won't. Wait. Okay, so the answers we got were 6 of these, 2 of these, 0 of these, 1 of these, 8 of these. Now I want you to talk to the people like you usually do. I'm going to draw a picture, though, before you do. Here is minus 2Q. Here's Q. Whoops, that's a G, but you understand. And we are given that we have, that is F, the force of the positive charge and the negative charge. And then we're asked, number 1, the direction, and number 2, the magnitude of the force on the positive charge due to the negative charge. So given that picture, discuss it with the people around you.
I think it's supposed to be the opposite.
Would it have to be 2 negatives? I guess wrong. It's right. It's right.
Negative charges.
Okay, let's go ahead and answer again. I think you haven't, well, mine, 2 people aren't registered with their clickers, but I show Lindsay and Bridget as not answering. So one of you 2, your answer isn't registered.
We have to re-register.
No. There we go. I'm not sure what happened with the with Ann's, but I know it has to do with her having multiple ones that I registered for her last semester. Okay, this time around, our answers were 3, 0, 0, 5, 9. Now let's answer this first on the basis of direction. What can you tell me about the direction between the force on one charge and the force on the other charge? They're opposite. Why do you know that? Because it's attractive, so they come together. What's another basic physics from first semester you could have used to come to that same conclusion? Well, in equilibrium, the sum of forces is 0. But Newton's third law says for every action is an equal and opposite reaction. In class, last period, I talked about if I were to hit Chad in the head, the force of my hand on his head would be the same magnitude but the opposite direction of the force of his head on my hand. So it has to be opposite direction. So we can immediately rule out the 2 up here that had positive because those are the same direction as the first one. Has to be negative. Now, of course, if it was 0, that wouldn't make sense. One's pushing on the other one's not pushing back. So now we look at the magnitude. How do we differentiate between F and 2F for the magnitude? Yeah. Newton's third law says they have to be equal and opposite. And so only this one here is equal and opposite. So Newton's third law gave us everything we need. We didn't need to know a thing about electricity. Now going to electricity, we have the equation, and I'm just going to show them, well, no, I'll show the whole thing. I'll show the vector. So that minus r hat is the part that tells us the direction, that tells us that opposites attract and likes repel. If I were to switch 1 and 2, what would happen to this part of my equation if I switched 1 and 2? It stays exactly the same because it's Q1 times Q2. If I change that to Q2 times Q1, that's still the same thing. Minus 2 times 1 is the same as 1 times minus 2. So that part stays the same if I switch the two charges. But if I switch the two charges, that's going to change the direction of the unit vector. Right? Because the unit vector is going from the first charge to the second charge. Well, if I change the charges, then it's going to be going from the second to the first, the opposite direction. So this equation also gives us the symmetry that says that the force had to be minus F. Imagine my surprise when I put in minus F and it said, no, you're wrong, it's minus 2F. And so, of course, I've reported that to them and they'll fix the problem eventually. This concept coach just came online at the end of December. So we are in the first people going through. So we are likely to find other mistakes along the way, which I'll be reporting, and I am hoping that they will find a way to fix this and retroactively fix the scores. Because, I mean, who wants to lose a point because you answered correctly? Yeah.
What about when these keep coming up on the review questions? I've had this question like 3 times now. Is that going to get kind of wrong every time now?
Only if you answered it as minus 2F.
Well, yeah, but that's what I did because I assumed that I was wrong the first time.
I know,
But
so
mine-
if it says it's right, when you guess negative F the first time, and then now you just say
So,
right,
yeah,
negative 2F.
you've learned the wrong answer because that's what they told you,
Yeah.
right? Yeah. Yeah. I don't know what to do. At this point,
After this point.
If you do it, you may.
Bring back reading quizzes.
Well, no, I'm going to stick with this because this is, I think, better pedagogy than the reading quizzes in general. Better for helping you learn the material. But we're having, things like this that it's anti-learning. That's why I'm showing you to make sure you get the right answer. I want to try to find an equitable way of having the grades. And so I will try to figure things out and how to fix it. Right now, there's not a lot of ability for me to go in and edit things. But I hope to get them to, fix these. Anyway, one more thing about these concept coach things that you may or may not have noticed is you get questions over. That is to reinforce. The research shows that if you have questions over a topic a week or two after you've covered it, it helps to reinforce the ideas better. You remember them better. So that's why you're getting repeats of the same questions. It's not a mistake. It's part of the pedagogy. And people are getting different questions. I'm not sure what their algorithm is for that. But just so I had one person who was concerned, it keeps giving me the same question. And it's part of the intentional plan. Alrighty, electric field. We talked about the electric field last class period, just introduced it. The electric field, what is it analogous to that we already understand quite well? The gravitational field, what we call the acceleration of gravity. The acceleration of gravity is exactly analogous to the electric field. Of course, the units of electric field are not the same as the units of the acceleration of gravity, because these fields are taking the force and dividing it by the charge the force depends on. So for the gravitational field, it was the force of gravity divided by mass, because that's the charge that mass depends on, or the force of gravity depends on. And so the units there were newtons per kilogram, or meters per second squared. Here, it's the force divided by the electric charge, so the units are going to be, what are the units going to be? Tell me. Newtons per coulomb. So the units of electric field are newtons per coulomb. And if I know the electric field, I can always find the force on any charge of random charge just by multiplying the electric field by the charge. Now notice we have a vector relationship here. So if I have a positive charge, how's the direction of the electric field compared to the direction of the force? They're going to be the same if it's a positive charge. Because I would have, for instance, if the electric field is to the right, 5 times to the right is still to the right. But if the charge is negative, minus 5 times to the right, what direction would that be? Be to the left. It'd be the opposite direction. So the force on negative charge is the opposite direction that a force on a positive charge would be. And the electric field is always pointing the direction that the force on the positive charge would be. So this brings us to the idea of a, quote, test charge. When we want to find what the electric field is somewhere, or what the force would be, we talk about a test charge, and we say, okay, if I put a test charge here, what direction is the force? And what is that test charge? That test charge is just going to be a +1. Why plus? So that the direction of the force is the same as the electric field. Why 1? So that we just have the electric field. So when we talk about test charge, we're saying if I put a positive charge here, what's going to happen? So test charge, that means I didn't actually put a charge here. It was a what if. Here I have a picture of a globe that has, what kind of charge do I have in the globe? Negative. Okay, so I have a negative charge in that globe. If I put a positive charge out here at position P, is that positive charge going to be attracted to the globe or repelled from the globe? It's going to be attracted. So what direction does that mean the electric field has to be at that position? Going in toward it. And so there is a fundamental rule for electric fields. Electric fields always point into a negative charge. Now, if this had been positive charges, if I put a positive test charge out here, then the force would be repulsive. And so electric field lines always point out of a positive charge. So fundamental rule, electric fields into negative charge, out of positive charge. Now, I'm going to go through a lot of slides worth of material while I'm on this slide, is the truth. Next thing. I have a conductor here. Let's say it's a solid metal piece. Solid metal, so I have conductor all the way through. Let us suppose that I have an electron that's here in the center of that globe. How do I know if the electron feels a force with respect to the electric field? Go ahead, say.
I was going to say, didn't we have that thing where it's like if it was a smooth metal thing, it was on the inside, then it wasn't working?
I'm getting to that. That's the reason we're talking about this. Yes, we have that. If there's an electric field in there, let's say there's an electric field pointing to the right, then what direction would the force be on that little electron? So if I have an electric field like this, then what direction is the force going to be? Then the force would be to the left. Because it's a negative charge, the force is opposite the electric field. What's the electron going to do if it has this force to the left? It's going to move. You have Newton's second law. The net force is mass times acceleration. So if it has a net force to the left, it's going to accelerate to the left. So it's not going to stay there. So now if the electron moves over here, it can only get this far, and now we're going to have that negative charge here on the surface. Now if I put the negative charge here, then that means electric field lines always point into the charge. And so this electron is making an electric field that's pointing that direction, pointing into it in the center. So what happened to the strength of the electric field in the center? Because that electron moved from the center to the edge. It went down. It got weaker. Now, if we have a conductor, there's a lot of electrons that can move. And as long as the electric field is not zero in the center of the conductor, what are the electrons going to do? They're going to leave the center. And so those electrons are going to move and redistribute themselves until you finally get to the position where the electric field inside the conductor is zero. That's the only situation where the electrons are going to stop moving out. And thus, for electrostatics, when we have static charge, we're always going to have the electric field inside of the conductor is 0. Because if it wasn't, then the conducting particles, the electrons, would move until they made the electric field 0. So the electric field inside the conductor is always 0. So let me write down my rules that we have here. And the opposite of that, electric field points into negative. And then we have the new rule, the electric field, inside the conductor is always 0. Now, if it's an insulator, that's not the case. Why is it different for an insulator as compared to a conductor? Yeah, the electrons can't move in the insulator. So you can have an electric field that's not 0 inside the insulator, but inside the conductor you can't. Okay, now let's get to the surface. And I know I have slides coming up, but let's just take an example. Let us say, what if the electric field on the surface here pointed like that? If the electric field points like that, what direction is the force on the electron there? The force on the electron would be opposite to that. So I would have a force on the electron that's going like this. Now that force, part of it would try to push the electron into the conductor, and part of it pushes it along the surface. Now we know that electron isn't going to go into the conductor because then that would change the electric field inside the conductor. So it's going to stay on the surface. But it can move along the surface, and so this electron would cruise around until it gets to a point where the electric field is not making it move side to side. So the only way the electric field is not going to make it move side to side is if the electric field is normal to the surface. So on a conductor, the electric field is always normal to the surface. So, actually, I write it down, then change it so you can't read it. These rules are simple rules, really, because we can see, oh, if that wasn't true, then the charge would just move until it becomes true. Each one of those, the charge would just, well, the bottom two, the charge would just move until it becomes true if it wasn't true. So when you reach a static situation where the charge has reached the stationary positions, you're going to have these conditions true. Any questions about how these come about?
So, an electric field is generated by anything that has a charge?
An electric field is generated by anything with a charge, yes.
What does it mean by electric field is normal to the surface?
Okay, remember the word normal is a three-dimensional word that's equivalent to perpendicular between two lines. So normal to the surface is coming out of the surface perpendicular to all lines you could possibly draw in the surface. Right? Technically, you're not supposed to use the word perpendicular because dimensionality is wrong. Oftentimes, books use perpendicular because students know the word perpendicular, even though it's misused. Okay, cruising through the slides. We are a full... Well, let's not worry about the percentage we are through the presentation because it's distressingly low. A point charge has a net charge of minus 10 nanocoulombs. What direction do the electric field lines point? Okay, that's looking good. Ah, somebody just changed to the wrong answer. This was, of course, just the rules we had. How do you answer it if you don't remember the rules? Because who memorized the rules that quick? You remember it just by saying, okay, I have a negative 10 nanocoulomb charge here. If I put a test charge, what can you tell me about the test charge? It's positive. So I put a positive test charge here. What direction is the force going to be? It's going to be attractive, so the force is like this. Hence, the electric field is the force divided by that test charge is going to have to be the same direction as the force, so into the negative charge. And so that was the correct answer, into the charge. Yes, go ahead.
So I guess what I was getting at earlier is you talk about the electric field.
Mm-hmm.
But in that situation, you introduce a second charge. So if you have multiple charges, is it each field belongs to each charge, or is there one field that's changed?
Chad brings up a good point. A charge doesn't self-interact, doesn't interact with itself. So if I'm looking at the electric field, I'm going to say, what is the electric field due to all of the other charges? And that's what this test charge, or a real charge that I put there, is going to see. So I have to add up the vector sum of all of the other ones. So it's not just an individual one, it's all of the others, but not itself. That's a very good point. Okay, once again, I'm not going to actually work this problem, but make sure we understand how you work it so you can do the problem. So what we have is an electric field that's pointing to the right. And we have a ball that's swinging out to the right. And we know what the distance it is out to the right and what the hypotenuse length is, hence we know what the angle is. And then we have three simple questions. What is the angle that the thread makes with the vertical? How would you find that, Anne? The Pythagorean theorem will tell you what the adjacent side is, but not the angle. Okay? Not the law of sines, but the definition of sine for a right triangle. And so, or you just like Chad, who knows that since sine theta is equal to opposite over hypotenuse, which is 6 over 12 or 1/2, then theta must be 30 degrees. So, you'd use the definition of sine for a right triangle. Remember, the law of sines was A over sine A is B over sine B. Okay, what is the tension? You could have used the law of cosines if you wanted. It's just a little harder. What is the tension in the thread? Well, how would you find the tension?
Presumably your sum of your forces is going to have to be 0.
Yep, if it's in equilibrium, we know the sum of the forces is equal to mass times acceleration, which is 0. And then we just show the forces as vectors. What forces are acting on that thing?
In the electric field, you also have gravity and force of tension.
Okay, force of gravity is simple. That's down, and that's equal to mg. The force of tension is always in the direction of the string leaving the objects. There's my force of tension. What direction must the force of electric field be here?
To the right.
It's got to be to the right. I know that because if it was to the left, I couldn't make them add up to 0. And so then I do my vector drawing, mg on this side, QE, because force E is QE, on that side, and try to make your picture actually match. And then force tension here, there's theta. I can find that tension pretty easily by relating the force of gravity and the force of tension. What trigonometric function is going to relate those? Cosine.
Oh, I'm sorry, I was looking at electric field.
because it's adjacent.
I was looking at
And then what is the charge in the sphere? How do I find the charge? I would go ahead, since I know this distance and this distance, I would use sine again. And say sine is equal to, sine of this angle, which is equal to 1/2, is equal to QE divided by the force of tension that I just found. And I would have my Q, since E was given. E was given right here. So it actually works out pretty simply. It's still just Newton's second law, right? It's just we have a new force that we're using. Any questions? I hate when I say it's simple, because then if you have a question, it's almost like I said, well, you're not going to have a question, right? Do you have a question? What is your question?
Wait, so the magnitude of the electric field then is QE. What number do we use for FE again? Or we just
Well,
solve for that using trigonometry?
FE is QE, and E was given here. And so I solve.
And then, okay, yeah. So I was asking how you get FE and FE, presumably then would be trigonometry, and then, okay. Yeah, okay.
Okay. Yes, by trigonometry. I thought you were saying Pythagorean theorem in my head. I was like, well, you can. It's a little extra step, but it works. All right. We've already seen enough of this. I'm going to go through a number of slides here that we've already talked about. This here goes to what Chad was asking about. The electric field at any point is the vector sum of all of the field vectors at that point caused by each charge separately. If you have a charge at that point, you're not counting it because it can't interact with itself. Okay, now an example problem that I think I will do. 2-point charges are located on the x-axis. Charge Q1 is plus 0.6 microcoulombs located at the origin. So here we have plus 0.60 microcoulombs. Q2 is minus 0.50 microcoulombs, and it's located at 0.4. And then we have some point out here, and it says, what's the magnitude and direction of the electric field at that point? How do we find the electric field at that point? We add the vectors, right? So I look at those vectors. What direction will the electric field be at this point due to the positive charge? It's positive. So if I put a positive test charge there, it would be repelled, which is to the right. So I'm going to have the electric field due to charge 1 is pointing to the right. What about the electric field due to charge 2? It's a negative charge. If I put a positive here at P, it would be attracted. So going toward it is like that. So I know the directions. So I'll have my electric field total is equal to E1 vector plus E2 vector. I'm just going to use signs for my direction because it's one-dimensional. So I'm going to use plus equals to the right and calculate these. So what is E1? If I have a point charge, I know that it's going to be that, right? I use Coulomb's law, and then I divide by the charge that I'm looking at. And the charge I'm looking at here doesn't really exist. It's a test charge. I was finding the force between the test charge and charge 1, but then for the electric field, I divide by that test charge, and it's just going to be K Q1 over R squared. And I better put R1 here, since I'm going to have 2 radii. So that's my E1. Likewise, my E2 is going to be K Q2 over R2 squared. And note that the signs here, if I have the positive charge, I have a positive sign in that equation, which in my picture is going to the right. So I'm just going to leave it that way. Remember from what I said last class period, the way I always work these is to actually find the magnitudes and then use my brain for the direction. So I can leave it that way, but I'm going to go ahead and make sure that I'm real clear, put a magnitude sign here, and so now I have the magnitudes of those two, and then to find the total, it's going to be the magnitude of the one to the right minus the magnitude of the one to the left. Whoops. There we go. And so that's equal to K magnitude of Q1 over R1 squared minus K magnitude of Q2 over R2 squared. Now all that remains at this point is putting in the numbers. Remember, I have magnitude, so the minus 0.5 microcoulombs in the calculation is just 0.5 microcoulombs. Question?
So on the second part on red, you subtracted it because it's going in two different directions?
That's right. I subtracted it because my arrows up here were the opposite direction. Plus was to the right, so I made the one that was to the right has a plus sign in that equation. Minus was to the left, so the one that was to the left had the minus sign. So I use my reasoning to put those signs in. Another reason why the pictures are so important. I'm not going to worry about getting numbers here. I think at this point we're all proficient enough we can put numbers in a calculator. And we have no further. And now what? So now a clicker question, I think. Yes. How do electric fields add? Please, please, please. Don't display. Okay. Thank you for making me believe they add as vectors. It's so simple, especially after the example we just did, to say, well, you just added the magnitudes. Well, I had to use the signs for the direction, so it was adding as vectors. The next example is very specifically as vectors. We had something, wasn't the same numbers, but exactly like this, where I worked out the problem in class, last class period. Now instead of forces, we're going to talk about electric field. What's the difference in adding the forces and adding the electric fields? We just divide by charge. So, what does the electric field do to these three charges at the fourth corner P? If I want to find it, how many vectors do I have to add? 3. And so I will write each one. Remember, I'm attracted, a positive test charge is attracted to negative. So I would have F3 goes like that. Repelled from positive, F2 goes like that, and, well, I should put the 2 in this. And repelled from that, so F1 goes like that. And so I have these 3 different vectors I have to add. What would you logically choose for your x and y coordinates? The ones I already made. You would choose horizontal and vertical. Why would you choose those? Yeah, because 2 of them are already in those. So you have 2 already resolved if you choose that for your directions. Any other direction is going to require more work. And we like to do minimal amounts of work. So now you just use the equation we did. Electric field is K, I'll put QX over RX squared. Do that for each one. Break them into their components. That's just the magnitude. I'll put it very explicit, the magnitude of EX and the magnitude of QX. And then you add them as vectors. Looking at my arrows, I would guess that it's going to go something like, so the resultant should be somewhere along the lines of like this. But that's just a guess. I have to put in the numbers to see what the actual values will be. We got 10 minutes left. Woohoo! Electric field lines. Electric fields, we've been drawing lines for electric fields. The concept of an electric field line is to say, okay, instead of drawing a whole bunch of little arrows here, there, and everywhere, let's just draw smooth lines that show how the electric field's direction changes as we go through space. And so at each point, to find these electric field lines, we're adding up the vectors of the electric field from each charge. And so we make continuous lines. Now let's see what these look like. Here is an example of some crazy curvy electric field line. At any point on that electric field line, you know the direction of the electric field. It's the direction of the line. So I can find the electric field at point P, it's going down and to the right. At point R, going up and to the right, because it's just parallel to the line. Notice the line has to have arrows on it to tell you which direction you're going along the line. An interesting thing about these electric field lines is they will not only tell you the direction of the electric field, they also tell you the magnitude in a relative sense. The magnitude of the electric field strength is inversely proportional to the separation of the lines. So if the lines are 1/2 the separation, the electric field is twice as strong. So you can look at this picture in the lower right and you say, the electric field lines, it's really unfortunate that they use green and green. Let's see, I have blue right now. Let's change to crazy magenta. I'll put magenta over these arrows so it doesn't look like that's also electric field. If we look at points P and R, the separation between electric field lines at point P is very small compared to the separation at point R. That means the electric field is much stronger at point P because the lines are closer together. Much weaker at R because they're farther apart. Simple enough? So here's what electric field lines look from point charges. We already learned the rule. The electric fields always point into negative charge and out of positive charge. Just based on symmetry, you could have said these are going to have to just be straight lines going out from the charge if it's isolated. These two pictures are pretending the other charge is not there, okay? If you have both charges there, it's the combination of two, you have to add them as vectors. Any surprises if that looks that way? I wasn't surprised either. Where is the electric field the strongest for the positive charge? See that, Alicia? Okay, right at the charge is the strongest. You know that because the separation between the lines is the smallest right at the charge. In fact, if those lines extended until they touched, you'd have a separation of 0 at the charge if it's a point charge. What would a separation of 0 suggest about the strength of the electric field? It's infinitely large. That agrees with our equation that said the electric field is equal to KQ over R squared. As R approaches 0, as your distance away from the charge approaches 0, the electric field approaches infinity. Another thing this tells you, you can count the lines coming out of this charge. It has 1, 2, 3, 4, 5, 6, and 6 is 12, right? That tells you about the relative strength of the charge. If this has 12 and another one only has 8 lines coming out of it in the same diagram, then the one with 12 lines coming out has more charge than the one with 8 lines by the ratio of 12 to 8. So you can tell the relative strength of the charge by the number of lines coming out of it. Yes?
Is it relatively arbitrary? So if I were to draw two things, like the one that has more charge, I just draw more lines on it?
Yes, because the spacing you choose is arbitrary, but then you have to be consistent throughout. So that's why you can compare. And so, for a simple charge, like if we have one that is, this one is plus Q and this one's minus 2Q, well, I'm going to make 6 come out of the plus Q and then 12 for the minus 2Q. So here is a picture that shows exactly that idea. I have a minus 2 microcoulomb and a plus 3 So that means that you have to have a 3-to-2 ratio for the lines. So this one here has 1, 2, 3, 4, 5, 6 times 2 is 12. And this one has 1, 2, 3, 4 times 2 is 8. 12 to 8, 3, 2. How did they find this funky shape? How does that come about? Vector addition of those vectors. So basically you take the picture each one would have alone, and then you add up the arrows at each point to get those lines. You had a question, Lindsay?
Well, I feel like in high school when I learned this, you could only have 8 on a thing or something. You could only have a certain amount of arrows on each one, but now you're saying it's arbitrary. So
Yeah, it's arbitrary. But you have to be consistent, and so you have to have the ratios agree.
So what I learned wasn't.
It was probably an artificial construct used to simplify things. This is impossible, as Ralphie Wiggum would say. You guys all know the quote, right? What? Me fail English? That's impossible. Why is that impossible? What does the electric field tell you?
Direction of charges.
Not the charge is pointing the direction it's the direction something is pointing that has to do with the charge. The direction the force on a charge is pointing. So if I have 2 electric field lines that cross, what direction is the force if I put a particle right there? Yeah. It can't have 2 directions. Hence, you can't have 2 electric fields cross. Remember, you are adding the electric field vectors up to find the total electric field at any point. And so, if I have them that look like they're crossing, I add them up and I get a different direction. So electric field lines can never cross. If they did, you would have to have 2 directions for your force at one point.
They could merge, right?
No, they can't. Well, they can merge at a charge. They can't merge in empty space. Okay, the idea of a dipole. Going to go through this a little quickly. If you have 2 charges that are separated, you have the dipole. 2 dipole. 1 positive, 1 negative. Let's look at an atom for an example. So I believe I should have a water molecule coming up right after this. I hope it's right after this. I edited and re-edited. Hopefully I remembered my order. Which statement is untrue about electric field lines? And that's not it, Jaron.
I gotta make sure I get my answer.
One of the statements has a subtle incorrect thing. People are slowly coming over to the correct side. Okay, let me stop now. We had 10, 4, 2. And the people in the big group were correct. Why was that one subtly incorrect? Right. If this was positive, it would have been correct. So the other statements, the electric field lines cannot cross, absolutely correct. Separation between electric field lines is proportional to the magnitude of the electric field. Now, somebody might have said, wait a minute, it's inversely proportional. If that's what you were thinking, then I'll take that. Because it should have been inversely proportional. My bad on that. I wasn't thinking it through. And then finally, the number of electric field lines leaving an object's proportional charge, definitely true. Okay. Here's the dipole. I'm going to end with the dipole. An example of a dipole. Wow. This is not the way I left it. I must have Made some changes that I didn't save again, just like with your stolus. An electric dipole occurs naturally in things like a water molecule. In a water molecule, you have the bond between the oxygen and the hydrogen that is not a nice little covalent bond. It has some ionic nature. And so what that means is that the electron is spending a lot more of its time with the oxygen, a lot less of its time with the hydrogen. And so you have a dipole. We usually think of a hydrogen as being a positive, okay, we usually think of it as a positive charge out here and a negative charge here for the electric dipole. Because if you take these two positives and add together, it's in the center. That electric dipole is very important for water for a number of reasons, and one is the hydrogen bond. The hydrogen bond is a bond that occurs between molecules of water just because you have a net negative charge on the oxygen and a net positive charge on the hydrogen. And that causes water, when it cools enough, to have a lower energy state if it forms up in this nice little pattern. But forming up in that nice little pattern actually makes the molecules spread out a little more. And by making them spread out a little more, it makes the density lower and ice floats. And so this whole dipole idea is really, really important to the way water behaves. If it didn't exist, what would happen to life on Earth? It would also not exist. Okay, we're done for the day. Have a swell long weekend. I'll see you in lab on Tuesday.